Hi there, so how are we doing? This is a chat about that black hole image which I hope you've been seeing, and later on we're going to have a GCSE request show and an A-level request show that I've got a couple of things lined up for already. This is the image. It's been created by over 200 scientists working on what they call the Event Horizon Telescope. This is the first ever image of a black hole, and I'm going to explain to you why you should care if you're a GCSE or A-level student. Not only because, well, this is an amazing thing and this is your reason why you want to do well. WWE plug, what do you mean, edit the title, what's up with it? Why should you care about this type of thing? You know, that's not really the type of question that I think needs asked. It's an amazing thing in the universe that you should care about, but why is it specifically worth you paying attention to this type of thing if you're a GCSE or A-level student? Let's have a little bit of context about black holes. Obviously they're in both specs, okay, but what they are or how we take photos of it isn't directly in both specs. It's normally about how they come about as a result of them being more massive than the sun. Okay, stars that have gone supernova, and have one of the outcomes of that is that you can have a black hole left behind. This object is 6.5 million times. Oh, thank you. Thanks, Kira. 6. Moving on. Hopefully that changes now. I've just got it. Yep, there. Thanks, Kira. Yeah, it should change now. That's embarrassing. Thanks, WWE plug. Anyway, moving on. This is an object 6.5 billion times more massive than the sun, so it's obviously it's going to go down that different route after after red supergiant than you know, it's not going to become a neutron star. It's going to become a black hole, and black holes are at the center of all galaxies, or all spiral galaxies anyway. They're all kind of flowing into, they're all being attracted to this black hole. This is in galaxy M87, and it is, I just wrote this down, 55 million light years away, and it needed a camera with a sensor as big as the Earth. Okay, it needed a telescope as big as the Earth. Now that doesn't mean we built an object as big as the Earth. It means that we linked up, or these people linked up, different telescopes that already existed into a sort of telescope array that is the size of the Earth. And I'm going to talk about why that's important. And why is it important for GCSE or A-level students is about those really tricky questions, those context questions. Now, context questions are when they ask you something that you do know about, but they ask it to you in a really difficult context, the one that you won't have come across before. And it tends to be some of the hardest parts of GCSE or A-level when you think to yourself, well, I have no idea what they're asking. This isn't on the spec. You know, this is not something that we've covered before. And you're absolutely right, it's not something you covered. So if they ask you a question about this black hole diagram, this image of a black hole, but there's going to be something about the thing they're asking you about it that you do know about. Some knowledge you do have that you can apply to this context. And actually we were talking about breaking down the things that you get wrong in exam questions, and the method of breaking down and looking at the ones that you got wrong. A lot of people find that the questions they get wrong are when they're trying to apply to a new context. They're trying to apply an idea that they should have to a new context. So that's the thing I'm going to talk about in just a little while. But I want to talk about, well, why does it need to be such a large telescope, and the idea of resolution. So let's talk about these things to get that idea. Let's talk about this. This is a camera. I'm going to go into the visualizer in just a little while. Okay, this camera is an absolute massive camera. Okay, this is a what you call a full frame camera, right? And that's a very expensive lens, and that is the sensor. That's the image sensor. That's what you call a full frame sensor. It's a very large sensor. So that's a large sensor camera. This camera, this one here, is what you call a micro 4/3 camera. It has a smaller sensor, but it's still quite a large sensor. Okay, and this last one is a GoPro. Okay, and it has a really small sensor. you know, in the region of a few millimeters size sensor in that one. Now they're all good for different jobs. They're all good for taking photos of different things, or videos of different things at different times. So let's just go back into this kind of view. Now this is the GoPro. This GoPro is great for outdoors, you know, fast action, things that are really quite close to us. This one is great for, you know, most purposes, but the real advantage to it is it's really quite small and light. But it still has a larger sensor than the previous one. So the important point is it can capture more light than the previous one. And this one is absolutely wonderful camera for taking indoor portraits of people, in indoor portraits and in low light situations. You know, I can take photos in, you know, like, I don't go to any clubs or anything like that, but in like night kind of dance, kind of disco kind of scenes, right? Because this sensor is so large, it captures so much light that you can get really detailed, high quality images of things when it's really quite dark. Just put the lens back on. Now, the point I'm trying to make is we're trying to capture, or they were trying to capture, an image of an object that was 55 million light years away, and they needed a very large sensor camera to do so. And that image, that light, is incredibly faint. You know, incredibly faint to us. It's light that is struggling to escape a black hole, for crying out loud. So that is, you know, that is an incredibly small object, an incredible distance away, that is not giving a huge amount of light in our direction. So you need a very, very large sensor to do that. Lane's made the point, yeah, they've already made the exam papers though, yeah, absolutely. But the point I'm trying to make is that you should care about these things rather than just know about this event horizon, this one telescope itself. We should care about these things because they can put these contexts into questions. Now I'm going to talk about some of the context they could draw out of this one, and I want you to think about, well, when you get that difficult context in the exam, try and think about the content that you can pull out of it, the kind of ideas that you can pull out of that kind of topic that they could actually write questions about. Now, there was an example in 2015, LIGO came out, and LIGO was the gravitational waves thing, and you know, they actually detected the waves, that the ripples in space and time, the gravitational waves that occurred when two black holes that were like spiraling around each other collided. And they made this kind of wave in space and time. So literally we're being constantly warped by these shifts in space and time, this you know, this rippling of space-time by these huge gravitational occurrences in our universe is constantly happening. And the question they asked was actually obviously not about gravitational waves, because they aren't on any specification at all, but it was actually about phase differences for lasers. Because the way that they measured those very, very small changes was to allow a laser to go over a very long distance, be reflected back, and compare it with a laser that hadn't gone that far, and look at its phase change. So the phase on a wave is how far along the wave you are. Okay, this is measured in a phase angle. So they can measure the size of a very, very, very tiny shift in the size of that arm that the laser had gone backwards and forwards on by phase change in lasers, and that is on the spec. So really, the difficult thing was about seeing the physics that you do know within this context. I hope that makes sense. Yeah. Anyway, I'm gonna crack on with some of these things that you could take out of this. I want to just briefly talk about resolution though first, because you know that's something that could come up, isn't it, on your specification. So I'm going to go into the visualizer really quickly, and far more kind of professional. If you want to know more details about this amazing bit of science that's just happened, then there are far more professionally made videos in the description that I've put for you to have a little look at as well. But resolution is a concept that you need to know about for practicals in GCSE or A-level, and resolution is like the smallest thing that it can measure. And the resolution of this camera, this Event Horizon telescope, is 20 micro arc seconds. Now later on we're going to talk about what we call parallax angle, and distances measured as a kind of angle from our view here on Earth. But I just want to talk about how small that is, right? And what tiny resolution this thing has. So, or high resolution, you could say, a tiny, smallest thing that it can measure, a tiny, small scale division that it can measure. So, an arc second, well, you think about 1 degree. Okay, that's a measurement of an arc, isn't it? That's an angle. 1 degree. Now, split 1 degree into 60 minutes. Okay, so degrees have minutes, like the scale, the division beneath each individual degree is in minutes. And then each of those 60 minutes, split that down into seconds. So 1 degree is 3,600 seconds. Okay, does that make sense? Now, if you think about that tiny portion of sky from our massive telescope here on Earth, that tiny portion of sky, split it into 3,600 seconds, and then have a millionth of that. Okay, so that's 1 arc second of sky, if you like. Do 20 times 10 to the minus 6 all over 3,600, and that is the fraction of an angle, fraction of a degree that it can measure. 20 times 10 to the minus 6 divided by 3,600 gives us 5.6 times 10 to the minus 9 of a degree. Okay, that's the resolution we're talking, and that's why they needed this massive camera. Yeah, it's the sneaky questions, Lane. It's the sneaky questions that we're worried about, isn't it? Right, arc seconds and things like that is on the spec, so I know if it's A level you're doing. Okay, right. Let's look at some other things they could tease out of this context. Okay, some other things generally related to GCSE and A level, really though. There's stellar evolution, so life cycle of stars, that's stellar evolution, and you know the idea, well, more massive stars, they are the ones that explode in these supernovas, and it's the really massive ones that become black holes. I'm going to do distance to black holes in the A-level feed later on, Lane, because it's one of your requests. Yeah. Okay, gravitational fields. They could talk about gravitational fields, couldn't they? So gravitational field strength is affected by 2 things. It's affected by the mass of an object. So we're on this big ball of stuff here on Earth, and therefore it has gravity. All things with mass attract other things with mass, and more mass, more gravitational field strength. Also, the smaller radius, the more gravitational field strength as well. So actually Jupiter has many times more mass than Earth. I can't remember exactly how many times, but loads. But it's only got 3 times the gravitational field strength because its radius is so much larger. Okay, and actually knowing gravitational field strength for different planets is on the spec, not knowing them, but knowing how to use them. And actually they could ask you to compare the gravitational field strength for this galaxy, this black hole, to that of a planet, and that would be, that would be quite a simple question actually, but you'd need to realise that, oh, they were asking to bring in knowledge that gravitational field strength on Earth is 9.81 newtons per kilogram, and that type of thing. Okay. So orbits, now the fascinating thing, I didn't really talk about this, okay, that image, a lot of people are going to think it's the image of the actual event horizon of the black hole, and it's really well done in the Veritasium video. But actually, you're not looking at the event horizon. Now, the event horizon is the point of like no return around a black hole. It's the point that if you go over that, there is no escaping that. There is no escape even for light. So a black hole is an object that's so massive and has such a small radius that its gravity is so strong that even light can't escape it. That's the event horizon. Now, we're not seeing the event horizon in that picture because well, the light won't escape the event horizon. So the event horizon is not something that can be seen because no light will come from it. But what you're actually seeing is the kind of next level, which is this kind of stable orbit of hot like gas and dust. And actually orbits is something that is in GCSE and in A-level. And you can think to yourself orbits as having like, there's a right speed for a right height. The higher you are, the faster you need to go. And if you're going too slow, then you'll spiral in and you won't have a stable orbit. And if you're going too fast, you'll spiral out and you won't have a stable orbit. What you're actually seeing is the light produced by this hot plasma around the event horizon. So you're actually seeing the first kind of stable orbit of the black hole. You're not seeing the event horizon. I think that's a really important thing. You're not even seeing there's a layer in between them where light is in a stable orbit. And you're not seeing that. You're not seeing this light in stable orbit because that light isn't leaving either. It's orbiting the black hole. It's incredible, right? So it could be the idea of like an escape velocity. You know, they could ask you to think about, well, what speed would you have to be going to get away from the black hole? And that's where this event horizon comes from. It could be about actually just, you know, a whole load of bump about the telescope, and then basically like, why do we analyze EM radiation, or like, you know, using the wave speed equation, telling you the speed of light is 3 × 10⁸, and maybe even that isn't fast enough to escape a black hole. What is the frequency of the light? The wavelength of the light that they are analysing is 1.3 millimeters. So it could be a case of just actually applying the wave speed equation to work out the frequency of that light, or thinking about different telescopes analysing different portions of the EM spec. So there's loads of different things they could ask you there. Do you want to quickly do this one? So 1.3 × 10⁻³ meters. Okay, so V is F lambda, that's V, that's the wave speed. So therefore frequency is wave speed over wavelength, 3 × 10⁸ over 1.3 × 10⁻³. 3 × 10⁸ over 1.3 × 10⁻³. 2.31 × 10⁻¹. Hertz. Okay, so that's the frequency of the particular light that they are analysing from the black hole. Okay, can you see how from this difficult context, you know, which is not on the spec, we've managed to get to things that are very definitely on the spec and that we need to know how to do. Okay, moving on, so very late to A-level, then you have this idea of like the gravitational potential at different points around massive objects. Okay, so you know, if I draw an object with mass and we draw its gravitational field, then we can talk about the potentials around it and how they are closer together. These are the equipotentials closer in, maybe. Okay, always draw our equipotentials at right angles to our field lines in whatever type of field we're doing. Could be about comparing fields. So, you know, maybe it's gravity is always attractive, but electric and magnetic fields always have attraction and repulsion because they have two different signs. So electric fields are between positive and negative, and magnetic fields are between norths and souths. So is it possible to have a black hole for a magnetic field? You know, that is the, what would you call that? What would it be? You know, so it could be a whole load of bump, and then really quite an easy question about just comparing magnetic fields with E fields and gravitational fields, G fields. Okay, next thing, well, it could be about light being affected by gravity, you know, light having mass, therefore, and this idea of general relativity. So this is general relativity, is what we're exploring right now with LIGO and this amazing telescope they've built. It could be about gravitational lenses. So the way that Einstein actually showed his thing was to show that light from a star that they knew was behind another star reached us. Okay, they knew we shouldn't be able to see this star because it's behind another star, but we could see it to one side of the star, and that's because light was being like refracted around it. So you think you've got one object in front of another one. Here's us here on Earth then. This is Earth. which is way smaller than the other thing, so I've not drawn that very well. But you shouldn't be able to see this star behind this star, but we could. And the reason for that is because that light was refracted around the object, so it appeared as if the star was here, but we knew astronomically that it wasn't. So it could be about actually gravitational lenses. So they could ask you like a lens equation. They could give you like here's a black hole acting like a lens. Draw a ray diagram. That could be a confusing way to bring in some of the on the spec that you should know and you do know how to do. Okay, I've talked about escape velocities, but it could be about different laws. So you have inverse laws with potentials, that's these lines around here, and inverse square laws for like forces. So if you put a mass here, then if you double its distance, then you get quarter the force, but you only still got half the potential. And it could be about collaborations. Why do we work in these massive teams? There's 200 or more people involved on this thing here, and it could be about actually using the idea of a angular diameter in astronomy, or maybe calculating a distance in terms of trigonometric parallax, which is using the idea of angles to give you distances. And we're going to talk about that later because I think Lane requested it. Hi Lane. We're going to talk about that later in our A-level live feed. Okay, there's just a couple more cool things that I want to say about this amazing thing, and then I'm going to say bye-bye until later. Firstly, this person I absolutely admire, Katie Bauman, was one of the most important people. She's a 29-year-old MIT graduate who was the person who came up with the algorithm that put all these things together. So all of these telescopes working together, they have to have something to take all that data to combine it into this amazing image. So it's absolutely incredible. I think I really hope that she gets a Nobel Prize, because she's written the computer code, which is the painstaking process really, isn't it, to put all that data together to give us that image. And then the last thing about that, well, the data from all those telescopes was too large for the internet, so we couldn't share all of that data. I keep saying we, like I've done it, but like it's one of those times that you're so proud of the human race. They couldn't share their data through the internet because there was so much of it that it would get corrupted, and they would, the transfers would take too long. So they actually flew it around on massive hard drives. So actually the amount of data that they produced must be like larger than the amount of data CERN produces, because the internet was invented for CERN scientists to share their data out into all these different universities, and yet this group of people have come along and made this incredible piece of work and made more data than the internet could really handle. I just think that's absolutely incredible. Okay, that's all I'm going to chat through on this topic. With this idea of be resilient, you're going to get these difficult contexts. You're going to find it hard to think, well, what is this really asking me about? What is it? Sorry, funny WWE. But you're going to find it hard to think of the different contexts, the different content within the context, and that's a challenge on purpose. They're doing that on purpose to you. So be used to, get yourself used to finding the GCSE or A-level stuff, the spec stuff, the knowledge within the context. And you can only do that by practicing. You can only do that by practicing applying your knowledge to things. So I suggest, maybe just read some popular stuff on the internet. I really like IFL Science, if you ever had a look at that. I used to just take that IFL Science and I'd stick it on the board in my class, 5-minute plenary at the end of the lesson, and I'd think, here's an interesting story in the media. What GCSE science could they relate to that? What A-level science could they relate to that? And if you get used to pulling in those ideas to explain stuff, then you're going to find it easier to do that in the exam. All right, I hope that helps. I always think that the strongest students are some of the ones who are going to read around the most, be most interested. So I would not read around because you're expecting those things to come up in the exam, although if it does, then that's great. But read around because it's just going to make you a more complete physicist, applying what you do know to these things. And most of these things, there is at least some level of physics that you do know that you can apply to this. All right, is there any chat that's sort of interesting? Just a minute. Yeah. Jeswin, this one was for GCSE and A-levels, really. Relativistic beaming effects. Yeah, that's why that. Can I explain relativistic beaming? No, I can't. I wish I could. I really. It's absolutely interesting. Apparently, like, so why is one side brighter than the other? Is the relativistic beaming idea. The why does it affect? Yeah, like, luminosity and not frequency. So it isn't Doppler shift, okay, but it is because it's coming towards us. So there you go. I apart from that, I don't know. So I know that's mentioned in one of the videos that I've linked underneath, but I think you're gonna have to find somebody with a higher level of physics knowledge than me to explain relativistic beaming. I know about standard candles though. We can talk about those later on. That's about luminosity and such. Okay, cool. GCSE folks, I will see you back at 2 o'clock if you fancy that. There's a few. What am I actually doing in that? I'm doing lots of interesting things. It's all in the description. I've got electricity, I've got radiation, and I've got life cycle of stars, and I've got magnetism as well. Loads of stuff for the GCSE one, and I've got stars. Sorry, I've got distances in the universe, and I have got what else was it? SHM coming up in the A-level one. All right. So thanks very much. I will see A-level kids at 4 and GCSE kids at 3.